Alright, so hello everyone, welcome to our first hands-on tutorial in the Introduction to Epidemiology with R series. Today we will learn the basics of R by exploring the data, summarizing the variable, subsetting the data or variable, visualizing the data using box plot, histogram, and QQ plot, some tests such as normality tests and equality of variance tests that are the main assumptions of some important tests such as t-tests, analysis of variance, or linear regression. And if not, we can use the non-parametric alternative test for t-test and analysis of variance. And finally, we will conclude with analyzing categorical variables using chi-square test and Fisher's exact test. So let's get started. So this dataset contains information on 118 female psychiatric patients. You can download the data from the descriptions. So each row here represents one patient and each column here represents one variable associated with that patient. So let's explore each variable. For example, the first one is patient ID, represent the unique patient ID. Age is the age in years for the patients. IQ score. Anxiety, so these are categorical variable. If the value is 1, it shows that anxiety, there is no anxiety. 2 means mild anxiety, 3 means moderate, and 4 means severe anxiety. And depression, if the value is 1 is none, if the value is 2 is mild, and 3 means moderate or severe depression. The next one is sleep normal, which shows that whether they are sleeping normal or not. If the value is 1, it means yes, they sleep normally, and if the value is 2, it means they don't sleep normally. The next one is lost interest in sex. If the value is 1, it means yes, and if the value is 2, it means no. The next one is suicide, which represents whether they considered suicide or not. 1 means yes, and 2 means no. And weight change, it's the weight change over past 6 months in kilogram. In this data set, the variables like age and IQ and weight changed. They are quantitative variables. However, anxiety, depression, sleep normal, lost sex interest, and suicide, they are all categorical variables. First off, let's load the data. Load data set. So I'm going to use read.csv because it's a CSV file. And I'm going to use file.choose and set the header to true. So file.choose here allows the user to load the data, which is great for beginners because you don't need to type the file path manually, which can be confusing for the beginners. And also we set the header to true to tell R that the first row in the data set in the CSV file contains the column names. And we are going to store this in an object, we're going to call it data. So let's run this line of code. When you click on run, it asks you where is the data. So you have to find the data. And you have to navigate to the folder that has the data, which is this one, and then open. So let's explore the data. So here also you can see the variables have been loaded into R. So let's explore the data. So the first thing that I'm going to do is I am going to check the class of the data. So what does it mean? So the class of the data can be data frame or matrix or list. And so if you run this line of code, the class of the data is data frame. And data frame is the most common structure for data sets in R and is like a spreadsheet. The next one is names of the data. Here, when you run this line of code, it returns the column and variable names. So these are the variable names. And then also you can check the n row, which is number of the rows in this data set, which is the number of the patients actually, which is I think 118. Yes, and then n col, number of the column in the data. In our data frame, when you run it, it is 9. So we have 9 variables, as you can see. I don't know why it's capitalized, so ncol, however it worked. ncol, run, still we have 9 column or variables. So the next one is summary. And summary, it provides a column by column summary of your data frame. And it depends on the type of each variable. So if I, for example, type summary of the data and run it, so it shows me the minimum first quartile, which means if I order the data from minimum to maximum, 25% of the variables are less than this. Median means that if we order it, 50% of the numbers are less than this value. Mean, which is average. Third quartile means 75% of the values are less than this, and maximum is the maximum value. But as you can see, it cannot differentiate between the quantitative variable or categorical variables. For example, anxiety, we had the values 1, 2, 3, 4, 5, right? 3, 4, and also we have some null values. So R thinks that these are quantitative variable because they are based on the numbers, but actually they're not quantitative variables. So for future analysis, we need to convert this to factor or categorical variable. So we will convert them to factor or categorical variable as we move forward. The next thing that we're going to talk about that is subsetting. So what is subsetting? So for example, if you want to have a subset or a slice or a specific part of the data, such as specific rows, certain columns, or both, we can use this square bracket for subsetting the data. Okay, so for the square bracket, so we have to put a comma. So before the comma, the values before the comma are for rows, and after the comma are for columns. Okay, for example, I would like to select the first 5 rows and all columns. Okay, so from data, I'm going to say that give me a subset of the data. The first 5 rows means from row 1 to 5, and comma, and if I don't mention anything, it means that all column. So if I click run, as you can see, I have the first 5 rows and all the column. Okay, so, or if you want to select, for example, the first 5 column. Okay, so in that case, I have to use all rows but the first 5 columns, and then run. So you can see all rows, only the first 5 columns. So how about if I want to select like row number 2, 4, and 6? So in that case, I have to combine these rows. So row 2, 4, 6, right? So I cannot type 4, 2, 4, 6 like this. So, and then all the columns. So here I have to put all of this. I have to concat all of these columns. So now it tells us that these are the rows, row 2, 4, 6, and column, all the column. So as you can see, 2, 4, 6, and all of the columns. You can also use the names of the columns. For example, I would like to select the age and IQ column, right? So from data, I want to have a slice of the data, all of the rows, but for the column, because we have 2 columns, I have to use C again. And then here I have to mention the name of the column, for example, age and comma, column IQ, right? And then run. So as you can see, we have column age and column IQ and all the rows. Or for example, I would like to select row 1 to 5 and age and IQ, right? So here I have to say 1 to 5 and age and IQ. So we will have 1 to 5 and then age and IQ. Or if you look at this, age and IQ are column 2 and 3. So instead of age and IQ, I could here type 2 and 3, right? 2 to 3. So we will get the same results. But if I want to quickly access a variable or column based on its name and then do further calculations on it, we can use $sign like this. So for example, from the data frame, if I use $sign, it automatically shows me all of the names of the columns, right? So I can, for example, select IQ. So data IQ means from data set of the data, select the column IQ. And then when you run, it shows me all of the values for the column IQ. And then you can also store it in the variable or object IQ. So when you do this, you don't need to, each time that you would like to call a variable, you don't need to, for example, write a data $sign and the name of the column. So you just run it with IQ. So let's, for example, do this for other variables. For example, from data $sign and age, I'm gonna store this in object age. And then for the next one, for the data $sign weight change, because this is also a quantitative variable, I'm gonna also select this into variable weight change. Run and run. So these are quantitative variables. So now let's convert all of the 5 categorical variables that we have into factor, because for the further statistical analysis, when we need to group it based on the categorical variable, we need to convert this to the factor, right? So for example, I would like to convert suicide here, right, to a factor. So first of all, I have to select the suicide from the data and then use as.factor to convert it to a factor, okay? So how we can do that? So I will say that from data, select, for example, let's start with anxiety. And then, so this is still quantitative variable. So I'm gonna say that as.factor for data anxiety, and I'm gonna select this as anxiety. So what happens is that when I run this, so now this is a factor variable that has 4 levels, 1, 2, 3, 4. So you can also check the levels for the anxiety. As you can see, we have 1, 2, 3, 4, right? So let's do this for other variables. So now if I take a summary of the, I don't know, like suicide, so what happens is that it doesn't show me the minimum, maximum, average, median, right? So now it shows the frequency. How many 1s do I have? How many 2 do I have? How many NAs or not available values I have, which is only 1. So in raw data set, missing values are normally entered as -99 or -999, right? For example, if you look at in the variable IQ, so you will notice that we have the value of -99, which is actually a missing value. But R cannot understand that this is a missing value and treats this as a number. So we need to tell R that every time you see values like -99, treat it as a missing value and mark it as NA, for example, like these values, right? So let's begin with basic stat. So I'm going to compare IQ values, so I don't need to type data $IQ because I already have done that, with -99. Okay, so what happens? So this command checks the values in the IQ column. If they are -99, it returns true. Otherwise, it returns false. For example, here we have -99. Here we have -99. Here we have -99. Okay, so I would like to select from the IQ column the values that the IQ is -99. Okay, so here I'm gonna select that from IQ column, select the values that are the IQ is -99, and then I would like to say that replace it with the value of NA or not available. Only select these values and then replace it with NA. So what happens when we run this? Now if I, for example, type IQ and then run this, so you can see that I don't have any -99. I have the value of NA that has been replaced by the value of -99. So I can also calculate mean, median, standard deviation, variance for each of the numeric variables that doesn't have missing value. For example, I want to find the mean of age. Okay, so click run. It shows me what is the average of the age. I would like to find the median of the age and then run, and also standard deviation of the age. I would like to know summary of age because it tells me all of these statistics, right? Minimum, median, mean, maximum, standard deviation, or I can also have variance of age, which is actually the square root of the standard deviation. So another thing is that I can be more specific and calculate age based on another categorical variable, okay? For example, I would like to compare the age for the group that have considered suicide or did not consider suicide. Okay, so here we had suicide, yes or no, and also we have age here, right? So in order to do that, we use by function. So by, so I'm gonna say that for the variable age, and then categorize it based on suicide, and then I'm gonna say, for example, mean, and then run. So what happens is that it calculates for the variable age, it categorizes it based on the suicide levels, which is 1 or 2, and then calculates mean. So the first argument is a numeric variable that we have. The second argument is a grouping variable, which is suicide or categorical variable. And the last one is, for example, a function. It can be mean, standard deviation, or I can also type summary. So I can compare the minimum for the people who had suicide or did not, first quartile, median, mean, maximum, and so on. Now let's move on to visualization. So the first graph that we would like to create is box plots. So box plot in R is used to visualize the distribution of a continuous or quantitative variable, and it shows the minimum, maximum, median, first quartile, third quartile, and also potential outliers. So it summarizes all of these numbers with just one graph. I would like to create box plot for weight change because it's a numeric variable, right? So I type just box plot and then weight change and then run. That's it. So if you zoom in, you can see that I know the minimum value, almost less than -2. I know the first quartile, I have the median, third quartile, maximum, and sometimes there are some like dots here that it shows the outliers, which are the values that are extremely different from the other values. So you can also identify the outliers using the box plot. Box plot is also a quick way to compare between groups. For example, I would like to compare weight change between people who committed suicide or who considered suicide or not, okay? So in that case, for the weight change, I separate it by suicide. So what happens is that if you click run, you will see that here we have two box plots for people who considered suicide or did not. And then I can compare the weight change between these people. I can also make this a little bit nicer. For example, we can add the XLAB or label for X variable, X axis, label for Y axis. I can also add a title to this. I can also change the color of this box plot. So let's do it quickly. So for example, here I can add XLAB or label for the X variable. I'm gonna say that considered suicide, and then YLAB, I'm gonna say weight change, and then also main, which is a title, I can say weight change by suicide consideration. And finally, I can color this, for example, to blue and red. Since it is more than two values, I have to use the concatenation C. So blue and also red, and I also have to close the other this parenthesis and run. So what happens is that I have the XLAB here, YLAB here, main here, and then color. So just remember that the first argument in the box plot is your quantitative variable, your numeric variable, and then separated by the grouping variable, which is the suicide. And then you can also add some more details. So this side-by-side bar plot allows us to compare the median. For example, for people who consider suicide, the median is higher than the people who did not consider suicide. The maximum is higher. The minimum is lower. So you can compare two groups side by side. Another important graph in R is histogram. So in order to create the histogram, it's very similar to the box plot. I just have to type hist, and then, for example, for the weight change, and then run. So it only creates the histogram for one quantitative variable. And that is also grouped into multiple bins that you can also change the bins, change the color, change the XLAB, change the YLAB, and so on. But another thing that you can do is that, for example, I would like to know the histogram for the weight change by, for example, if they consider suicide, and also if they did not consider suicide. So in order to do that, I have to slice the data, slice this histogram, only considered if they the value of the suicide was double equal to 1. So what happens is that it only creates the histogram for weight change if the suicide value is 1. And then click run. So here is for the suicide value is 1. And then for people who their suicide value is 2. So you can compare the histogram for people. So another important plot that we use to check the assumption of normality is quantile or QQ plot. In R, we use QQ norm and QQ line functions. So for example, QQ norm, for example, for weight change. So click run. So here creates a QQ plot. We also have to add the QQ line for the weight change. So what happens is that it adds a line to this graph. And if the points here are roughly follow the straight line that you can see, the data is approximately normal. But if the points curve away, it indicates skewness or non-normality. So the QQ plot can be used to check the normality assumption of the data. For example, here also you can say that I would like to have the QQ plot for people who had suicide or people who did not have suicide. So in that case, I can add, for example, slice it based on suicide double equal to 1 and suicide double equal to, and also you have to add this to the line double equal to 1. So that is another plot, right? So here is different, only for people who had suicide, and also you can have it for people who did not consider suicide. So 2 and 2. So as you can see here, the points are roughly follow the straight line, so the data is approximately normal. But many statistical tests, such as t-test, ANOVA, linear regression, assume that the data or the residuals of the data are normally distributed. And to verify this assumption, we can visually do that using, for example, histogram or QQ plot that we just saw. But also we should run a formal test like Shapiro-Wilk test. So test of normality. The null hypothesis here, so H0 or null hypothesis, states that the data follows a normal distribution. An alternative hypothesis states that the data is not normally distributed. For example, we would like to test whether weight change for each group of suicides is normal or not. Okay, so for example, for the group of the suicide equals to 1, for it equals to 2, we would like to test it. Okay, we would like to conduct a formal test. So in order to do that, we use Shapiro-Wilk test, and it's only Shapiro.test. And here I'm going to say that for weight change, right? So I can say that, so here test whether the distribution of the weight change is normal or not. And here, as you can see, the p-value is greater than 0.05, which cannot reject the null hypothesis. So we accept that the distribution is normal or doesn't significantly deviate from the normal distribution. And it's likely normally distributed. But also you can check this for example, not for all of the weight change, but also for people who consider suicide. So for people who consider, because you have to conduct this for each group. So for people who consider suicide, the p-value is greater than 0.05. So it is not significantly different from normal distribution. And also for the other group, look at the p-value is greater than 0.05. So we cannot reject the null hypothesis. We accept that the distribution is normal. And also many statistical tests like t-test and ANOVA rely on equality of variance or homoscedasticity. So here type test or equality of variance. So the null hypothesis here states that we have equal variance. So it is for groups between multiple. When you have multiple groups, you would like to see whether their variance is equal or not. And the alternative hypothesis states that it's not equal variance. So as you know, a null hypothesis always contains equal sign, and alternative never contains equal sign. I would like to compare the variance between the people, variance of the weight change between people who consider suicide or did not consider suicide. The test that we will use is called Bartlett test, and then it is weight change. So the first one is the numeric variable, and then I say that's separated by suicide. So that's it. And if you click run, so you can see the p-value is greater than 0.05, so we cannot reject the null hypothesis. So we can say that both groups, suicide yes or no, consider suicide yes or no, they have equal variance. So the equal variance assumption is satisfied if you want to, for example, run the t-test or ANOVA test in the future. All right, so now that we check the normality and equality of variance assumptions, we can proceed to conduct t-test and ANOVA test. So the first one is t-test. So t-test compares the means or average of two groups. So for example, I would like to see if there is a significant difference in mean of the weight change between the two groups that consider suicide or not. Okay, so we have two groups, suicide or not, and also I would like to compare their weight change, which is the quantitative variable, the average of the weight change or not. Okay, so the null hypothesis again states that there is no difference between the groups, no difference between, here is mean of weights, and the alternative hypothesis or H1 represent that there is. So in order to run the t-test, it's very simple, t.test, and then your numeric variable, which is weight change, and then I'm gonna say that's separated by what? By suicide, right? And that's it. And here also you can say that, for example, var.equal, so you can say that the variance is, you have already checked that the variance between these two groups is equal. So when you run this test, so here you can see that it's a two sample t-test, and the p-value is greater than 0.05, so we cannot reject the null hypothesis. So we accept that there is no difference between the mean of weight change between people who consider suicide and people who did not consider suicide. Sometimes you may say that, okay, so maybe when I run the Bartlett t-test, I see that the variance is not equal. So what should I do? In that case, you have to set the var.equal to false. And when you do that, it will run Welch t-test. Okay, so when you run this, so you can see that it will run Welch 2 t-test, which means that the variance are not equal between the two groups. And again, also you can see that there is no difference because the p-value is greater than 0.05, so we cannot accept the alternative hypothesis. We cannot reject the null hypothesis. So we have to say that there is no difference between mean of weight change between the people who consider suicide or not. So how about if the normality assumption couldn't be met? So this one is a Welch t-test. If the equality of variance cannot be met, but sometimes normality assumption cannot be met. So in that case, we have to use a non-parametric alternative to t-test, which is Mann-Whitney U-test, also known as Wilcoxon's rank sum test. So not normal groups. So because you have to do this for each group, right? So they should have a normal distribution. In the Mann-Whitney U-test or Wilcoxon rank sum, first of all, it doesn't assume normality, and also it compares the median or distribution ranks between the two groups. It's not based on the mean. So in that case, so when the null hypothesis is gonna be, there is no difference between median of the, so here it's gonna be median. And here also the alternative hypothesis here is gonna be based on the difference of the between median of the weights. Okay, so it's very simple to run this test. Just type Wilcox.test, and weight change is going to be very similar to the t-test. Weight change separated by suicide, and then run. So as you can see, it runs this test, and also the p-value is greater than 0.05, so we cannot reject the null hypothesis. So there is no difference between the median of the weights. So first you have to check the normality assumption. For example, use the QQ plot. You can see that it's not a normal distribution, or you can use the Shapiro test and you can see that the distribution is not normal. And then you have to use the non-parametric alternative of t-test, which is the Mann-Whitney U test that we just saw. Here we had only two groups, and we compared the mean or median of the two groups, right? But how about if you have more than two groups? So in that case, we have to use ANOVA. So ANOVA, and t-test is actually a special case of ANOVA, and ANOVA is more general framework that is used to compare the means of a continuous variables across more than two groups. And when comparing means between only two groups, a t-test or ANOVA will give you the same results. So for example, I am interested in examining how weight change differs across multiple depression levels. So if you remember, for depression, we had more than two groups, 1, 2, 3. Here, as you can see, we have values are 1, 2, and 3. So more than two groups. I want to see for the group of 1, the mean of the group of 1, mean of the group of 2, mean of group of 3. Is there a significant difference between the of the weight change depending on the depression level? Okay, so in that case, we have to use the ANOVA, and the null hypothesis here states that all means are the same. Okay, and alternative hypothesis says at least one mean is different than the other. So how we can run this is very simple. We have to use AOV, and then again, the first variable is your numeric variable, and then separated it by your dependent, by your grouping variable, which is your depression, right? And then run this. So you have to here make sure that the depression is a factor variable, as you can see. Otherwise, you will not get the true results. Okay, so we already have prepared this. So R knows that this is numeric and this is a grouping variable. For your data, you have to make sure that this is a factor variable. So again, let's look at the p-value here. So how can I see the p-value? I have to store the result. So I'm going to call this result1 or res1, and then run this and take a summary of the res1. And here you can see the p-value, fs statistics, and also the mean. Here you can see the p-value. As you can see, the p-value, it shows that there is no significant, it shows that we cannot reject the null hypothesis. All means of all of the weight change between all of the depression groups are actually the same. There is no significant difference between them, okay? So as we said, ANOVA assumes that the distribution of each of the groups is normal, and also they have equal variance, right? And also we have independent observation. But if these assumptions couldn't be met, what we have to do, we have to use a, similar to t-test, we have to use a non-parametric alternative for the ANOVA, which is a Kraskov-Wallis test. And Kraskov-Wallis test compares median. So not an alternative, but it's going to be similar to the ANOVA test, right, for the Kraskov-Wallis. But here it's going to be based on the medians, and at least one median is different. So if you check the distribution, it wasn't for each group, it wasn't normal, or they didn't have the equal variance. For example, you run the Bartlett test, you have to use the non-parametric of the ANOVA, which is the Kraskov-Wallis. So if you type Kraskov test, it's going to be very simple. So weight change, and then separated by your grouping variable, which is depression, and then run. So as you can see, again, we cannot reject the null hypothesis. All the medians are the same. And lastly, let's talk about categorical variables. So when both variables that you have are categorical variable, for example, smoking, yes or no, and income bracket, low, medium, high. So they are categorical variable. In order to analyze it, the first thing that we have to do, we have to create a frequency table or contingency table to count how many observations are in each cell, and then test the association between these two categorical variables. Okay. So suppose that we would like to examine the association between suicide. So here you can see suicide is a categorical variable, and also depression. So I would like to see, is there any, and also we already have converted them to factor, right? Depression and also suicide. So both of them are categorical factor variable. I would like to see, is there any association between suicide and depression? So for suicide, we had 2 levels, yes or no, 1 or 2. And for depression, we had 3 levels. 1, which is low, 2 is medium, and 3 is high. And we would like to see is there any association between them or not. So the first thing that the null hypothesis here is that there is no association, right, between the categorical variable. An alternative hypothesis shows that there is a statistically significant association. Okay, there is association. So the first thing, as I said, we have to create a contingency table. This gives us a 2x3 table because for the suicide we had 2 and for depression we had 3 levels, right? So I will type table and then suicide and then depression and then run. So here it shows number of the cases for different, for example, suicide and depression, suicide, depression level 2, depression level 3, right? Depression level 1, 2, 3, and then, so this is the contingency table. So I'm going to save this in an object called table 1, right? And this is going to be the input for our chi-square test. Okay, so for example, if I run the Pearson chi-square test, it's very simple. Chi-square.test, and then that's it. Table 1 is going to be the input. When you run this, so the p-value is very, very small. It shows that it's very simple. So we reject the null hypothesis. We reject that there is no association. We accept that there is association between the depression and also considering suicide. Okay. As you know, one of the assumptions of the chi-square test is that all of the expected counts should be more than 5 or more than 10 because this is a Pearson chi-square test, right? So how can I check the assumption that the expected count is greater than 5 or not? So in order to do that, you have to, so let me save this in another object, for example, res2. And then from res2 here, use $sign. And here you can see the expected values. Okay, so when you run this, so you can see all of the expected values are above 5. So we can actually use the Pearson chi-square test. But if the expected value was less than 5, we could not use the chi-square test because chi-square in that case overestimates the significance. And in that case, we had to use Fisher's exact test. For example, I would like to examine the association between anxiety and depression. Okay. So here, if you look at the data, we have anxiety, there are multiple level, and also depression, there are multiple level. So I would like to test the association. So definitely you're going to have very some small expected value. Okay, so again, table between anxiety and depression. So I'm going to call this table 2. Table 2, do not use a space, run. So, and if you look at the, if you run the chi-square test for table 2, let's see what happens. So you can see that you got a warning that the chi-square approximation may be incorrect. And why is that? Because if you look at the expected count, definitely you will see that it has very low values. So let's check the expected count. For example, here is going to be res3, result 3, and then res3, and look at the expected counts. So as you can see, we have some expected counts that are less than 5, here less than 5, less than 5. So that's why we got a error. So in that case, instead of using the chi-square test, I have to use the Fisher exact test. Okay. So if I use Fisher exact and table 2, and then now let's see the results. So let res3. So as you can see, the p-values are very, very low. So, and also you can see it runs the Fisher's exact test for count data. And also the p-value is very, very small, which shows that there is a significant association between anxiety and depression. But remember that the Fisher's test, it doesn't show you the expected counts. If you run the expected, it will not show you the exact expected count. But as you saw, the expected counts were small, and we can run the Fisher's exact test, that it showed that there is a statistically significant association between these two categorical variables.